So in the Tolman and Stewart experiment, what they're looking at is trying to figure out, what were the charge carriers in metals. And so they knew that, charge would pass through, but, they were trying to figure out exactly what it was. And so they came up with an experiment to test it, and essentially, and this was 1916. In 1897, J.J. Thomson discovered the electron. So what they did is they, based on inertia, right? If you drag metal bars or something like that, the charge is going to have inertia, and it's going to lag behind. And so, with the inertia, they were able to figure out that electrons were actually the charge carriers in materials. And yeah, I'll go ahead and pause the clip and read this caption here about how they did that. I'll give you a little bit more detail, and when you're ready to continue, you can hit play. All right, so the electrons stayed back, making one side more negatively charged, and it proved their theory. All right, so let's go ahead and practice electric fields with a long metal conductor on the top and bottom here, and we want to draw what the field might look like. So yeah, I'll go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so remember how we draw fields, right? We place a positive test charge and then see where it goes. This would be, straight down here. Up until you start to get out here, and then if you have an electron or a proton out here where you see what the field's going to do, it would swing around like that. One of the things that is important to take a look at with conductors is that there's no field inside. And so, you maybe heard of the, like a Faraday cage or Tesla cage where you have a conductor on the outside and a person is inside. And so you can have electricity go to the conductor on the outside and there's no field inside. And yeah, and so that's an important thing to remember. So voltage is a really important topic, and we introduced that, last year, and worked through that. And it's important to, make sure that we remember what's going on with that. If we have a uniform field and we push a charge across, right? If we apply a force over a displacement, we're doing work, right? And we do work as from there to there, force over displacement. So we have the potential difference then is the work done per unit charge from moving a point charge from one point to the other. And we look at that as, how much work is done, and we divide it by Q, the amount of charge that we have, and we can figure out, the voltage that takes place. So in this case here, we take a look at the potential difference, and the path does not affect the work done. So in other words, if we take this charge and we, go down and then up and around and whatever, and then get to here, that's the same as just going straight across. The only, amount that counts is going, directly against the field. So what we want to find out here is how much work does it take to do this. This is 25 volts from here to here. We have a 2 microcoulomb charge. And yeah, go ahead and calculate the work done. So go ahead and pause the clip and give us a try. And when you're ready to check, you can hit play to continue. All right, so we've got voltages work over Q, and we can multiply in the voltage times Q, and so it would be 5 times 10 to the negative 5th joules would be the work that would be required to bring it from there to there. And again, if we did this, same amount of work, and because it's independent of the path. All right, so if it takes 1.5 times 10 to the negative 4th joules to move a 2 microcoulomb charge from here to here, what is the potential difference? In other words, the voltage. So go ahead and pause the clip and give this one a try, and when you're ready to check, you can hit play to continue. Okay, so it should be 75 volts to go across. All right, so we have Q for the electron here, 1.6 times 10 to the negative 19th coulombs. And let's say that this is going over 1 volt. So the electron volt, which is a very critical value that idea that we talked about, is the work done when a charge equal to 1 electron is taken across a potential difference of 1 volt. And so it's, if we have voltage is how much work is done over Q, and we arrange that. And so 1 electron volt, therefore, is 1.6 times 10 to the negative 19th joules. And that's 1 electron volt. Now, you don't have this on your equation sheet, but you do have the charge for an electron. So if you remember, this number is how many joules 1 electron volt is. That will be really, really helpful for you. All right, so let's take a look at this one here. A proton is accelerated from rest through potential difference of 5,000 volts. What would be its final velocity after going through this potential difference? And then part B is determining the potential difference required to slow it to half its speed. So go ahead and try at least part A, and then we'll take a look at part A first, and then you can try part B. So go ahead and pause the clip and give part A a try. When you're ready to check, you can hit play to continue. Okay, so here's our potential difference, 5,000 volts, and it starts from rest. V is work over Q, and so we have the voltage, 5,000 volts times the charge. It's going to be 8 times 10 to the negative 16 joules, or 5,000 electron volts, right, is the energy. And therefore, all of that is going to go into kinetic, which will give us a speed of 9.79 times 10 to the 5th meters per second. So now we want to find out what is the potential difference required to slow it down to half its speed. And so, yeah, go ahead and pause the clip and give that a try. And when you're ready to check, you can hit play to continue. Okay, so half the speed would be 4.89 times 10 to the 5th. Therefore, it would take 2 times 10 to the negative 16 joules to do that. So we can figure out the loss, and that would be 6 times 10 to the negative 16 joules. And therefore, it's going to take 6 times 10 to the negative 16 joules to slow it down to that speed. Therefore, it's going to be 3,750 volts to bring it down to half its speed. All right, so let's try this one here. This is a former IB question. Electron is accelerated from rest in a vacuum through a potential difference of 2.1 kilovolts. Deduce that the final speed is 2.7 times 10 to the 7th meters per second. So yeah, go ahead and pause the clip and give us a try. When you're ready to check, you can hit play to continue. Okay, so 2100 volts is going to be 3.36 times 10 to the negative 16th joules. And we can figure out, that the final speed will be 2.7 times 10 to the 7th meters per second.